where things left off, back in the world of how things work, is looking at electric power distribution. And really just the opening story I talked about a Friday ago. And so here's the problem. I'll remind you of the problem. And that is that if you want to deliver electric power, we know things like you need two wires, right? You need a wire for the charges to go in carrying energy, and you need another wire for them the charges to come back without that energy to send them through again. So you need a circuit to begin with. But if you want to deliver a lot of power, and you want to deliver it to some distant users, the wires matter a lot. And you can send a large amount of electric power sort of in two extreme forms and everything in between. The extreme forms are a large current of electric charges with a small voltage difference between them. So you send the current out with the charges, each charge not carrying very much energy, electrostatic potential energy, but send an awful lot of them every second. So send them out with a small amount of energy per charge, that's a small voltage, but lots of current. So there's lots of charges going through the wire on the way out to the user. The user takes the energy, returns the charges to you as a large current at a somewhat smaller voltage than it arrived in, having had energy taken out of the charges. So that's one delivery approach. Large current, small voltage difference between the two, the current that arrives and the current that departs from the user. Any questions, issues about that idea? Large current, small voltage, it's okay? The product of the current flowing times the voltage drop at the user is the power that's delivered. So the other extreme is go for a big voltage drop. Send the charges out chock full of energy per charge. That is big voltage, high voltage. And take them back at very low voltage. So that each charge drops off a lot of energy, and then you don't need as many charges going by each second. You're sort of using each charge more effectively. So a small current with a big voltage drop. And the product of voltage times current, again, the voltage drop times the current, it's big again, yay, lots of energy delivered. And so these two approaches look just seemingly indistinguishable. Who cares? They're both fine. Well, there are problems with both of them. The one where you send a huge current with a little voltage drop has problems in the wires themselves. And that's because wires are consumers of electric power, whether you like it or not. They need a voltage drop in them to create to be the electric field that pushes the charges forward through the metal, because ordinary metals don't carry current for free. They need the current slows to a stop. It's another inertia. Yeah, inertia would be great, except that there's sort of a friction-like effect in the wires. So if you try to send a large current through a wire, you need a pretty large voltage drop across it to get that current going, to keep it moving through the wire. And if you look at the power consumed by the wire itself, it's a little bit of manipulation of the numbers. It turns out to be proportional to the square of the current in the wire. It's actually the resistance of the wire, the electrical resistance of the wire times the square of the current. That's specifically. So if you double the current in the wire, you quadruple the power the wire itself chews up. And this is a problem. It's a real problem that we deal with. Well, the society deals with routinely. Something like 6% of the generating capacity of the US is consumed in the wires delivering the power. So it's a non-trivial amount already, and you certainly wouldn't want to, if you just doubled all the current in all the power lines, you would quadruple the power waste. You'd go from 6% to more like, it would be 36% of the first number, but it's going to be 18%. You probably have to divide by 2 because you've doubled the power. But anyway, it gets to be a large fraction of the power generating capacity of the country. So not a good idea. So what do you do? Well, that is the problem with the high current, little voltage drop approach. How about the high voltage, little current approach? The power waste in the wires is much smaller. This is great. The current, because you've reduced the current in the wires, And because wires waste power according to the square of the current, proportional to the square of the current, dropping the current dramatically is great. The wires are not nearly as severe consumers of the power. The problem, though, is that when it comes time to deliver the electric power, you do not want two wires arriving at your house, one showing up at 100,000 volts, the current's coming roaring in 100,000 volts and leaving your house at 0 volts. That voltage drop is dangerously large. It will lead to lightning bolts in your house. It'll start fires, basically, or worse. So there's a conflict between these two approaches. Neither of them is ideal. So what has evolved and what finally, Edison tried to sort of balance off these two problems strategically by, you don't want to use a huge current because you waste a lot of power in the wires. You don't want to use a huge voltage because you'll light fires everywhere. So you go in between and you try to get it just right, and he tried and he couldn't do it. Instead, the system that evolved uses a hierarchy of voltages, which is what this view graph's about. And that is that power is transmitted long distances at high voltage with modest currents. So they're using that trick. They're using that wonderful feature of electric circuits that if you drop the current, you can send a lot of power, but you can still send a lot of power, but you have to have big voltage drops around. So transmit the power long distance at high voltage. And that's, you see these high voltage transmission lines. Obviously, people don't like them in their backyard because they're all worried about them and stuff. And I would say they're not particularly attractive, but there's no real evidence that they're any hazard. Except for the wires dropping, falling on your house. But basically, that's how power moves across the country, long distances. It's very high voltages with modest currents. And then for delivery to your house, and even delivery to the neighborhood, there is an effort made to shift the power into different circuits where the currents become larger and the voltage differences get smaller. By the time it shows up at your house, the current's quite large and the voltage drops are quite small, so it's safer. You can deal with this again. Questions about the idea about that hierarchy arrangement? Silence again. All right, well, whatever. The big trick then is how do you move the power from one of these circuits to the other, and even what does it mean to have more than one circuit? So if I'm trying to convey to you some understanding of how our electric power grid works, I want you to understand, when the dust settles, the idea that there really are separate circuits. There are separate racetracks for electric charges that do not electrically connect to one another. And power is moved from one of those circuits to the other without any electrical connection between them. And the power comes roaring across country in a circuit that involves very high voltages and small currents, or modest currents at least. And it works its way into your neighborhood as larger currents with smaller voltage differences across them. And it works in your house in circuits that have large currents and small voltage differences. And the fact that the power is moving from circuit to circuit is kind of amazing. How does this happen? You've never had a situation where you've got a flashlight sitting over here glowing with, switched on, glowing away, and you put another flashlight over here, and you do something, and the power leaves the circuit over here in this flashlight and starts illuminating that flashlight. How did that happen? There's not an obvious way to have that happen. But it does, that kind of idea does happen. It moves, energy is moving from circuit to circuit by way of electric and magnetic fields. And so, to some extent, this is one culmination of this story I've been trying to build of electric and magnetic fields. We saw them in simple context first and stuff, and very independent of one another. And then they started to overlap a little bit when we started playing with electromagnets. This magnet here, which is always fun to play with, as long as I don't shock myself. This is getting to be reasonably high enough voltage that I do not want to play games with it. But this is now, was a strong magnet for a minute. Probably blew a circuit breaker or something. Try plugging it into. Yeah, that's better. Okay, physics was saved again. This is using electricity to create magnetism. Wow, you know, it really works. The other thing is creating magnetism, which involves building a magnetic field around these objects. Before I turned it on, which I did by accident by plugging it in rather than by closing that knife switch, there were no magnetic poles here, and therefore no magnetic field. When I turned this on, there was a process of building that magnetic field up, creating the poles, essentially pulling apart norths and souths. So I don't know, this might be north, that might be south. I've never been sure which is which. But anyway, so one of them is developing north pole, one south. There's energy involved in tearing those poles apart. And it's the same energy that lives actually in the magnetic field itself. And I've never talked about that before in either electric or magnetic fields, but the fields themselves actually contain energy. And that will become more important as in the near future. I mean, the idea become more important in the near future because eventually we will make or observe features, structures in nature that consist only of electric and magnetic fields, nothing else. What's an example of such a structure? A radio wave or a light wave, which are they're total relatives of one another. They're the same thing. They differ a little in details. But basically, light and radio waves, they have nothing else except electric and magnetic fields, which is, you know, how does that work? Well, we'll get there. But the point is that they carry energy. You know that light carries energy because it comes from the sun and does interesting things here. It heats things up, it creates solar energy, all that. It's carrying energy. Where's the energy? Well, it's en route. It's in the electric and magnetic fields. So, having said that, then, go back to this much more pedestrian example. We just built a magnetic field by turning on this electromagnet. It was built with the help of electricity, and that means the electric company delivered some energy to this baby in the process of sort of powering it up. And that energy is still here. There is some energy that is being wasted as thermal energy because the wires are continuing to carry current and they are not perfect. And as with all wires, you have to push the charges forward to keep them moving. So there's some energy just being wasted basically as a little space heater just because the wires are imperfect. But the initial burst of energy that came in here did a much more interesting thing. It did not go into thermal energy. It went into building the magnetic field. And that energy is packed here, and if you want to see it, we can take it back out of the magnetic field. When we let the magnetic field not dissolve, diminish, everything go back to the way it was, the energy will come back out of these. And there are ways in which we could send it back to the power company, but it's much more fun to keep it locally and turn it into a flaming arc here at the knife switch. So the energy that's going to come back out of the magnetic field, the details, do they really matter? On the grand scheme of things, no, you won't remember them anyway. But there is energy in the magnet. It took energy to store it. Here it comes. Watch the flaming arc there. That was the energy coming back out. Is it okay? It's a real effect, and substantial amount of energy in this. Just because I can tell you about it. Many years ago when as a kid, I was always scavenging electronic parts. I was that kind of kid. And on my bicycle, go down and get these great traffic controllers were being thrown away. Oh man, great, the light switches, all this. And I got this object that had 2 wires and nothing else. And what is it? I don't know. So I took my a meter that's meant to measure characteristics of any electrical device, like electrical resistance, for example. And I, with my 2 hands, grabbed the 2 wires and the 2 connectors for my ohm meter and touched the gadget. And the needle on the device that measures resistance slowly went to a certain point and settled. That's odd. And as I was taking the thing apart, I got a tremendous shock. as the magnetic field that I had created in this object, which I didn't know what it was. It's called an inductor. It's basically an electromagnet. It had stored all that energy in the magnetic field inside this. There was a coil of wire in there and a chunk of iron. And it was all stored in there. And when I undid the storing process, it released all that energy, and I became the flaming arc for a second. Oh, that was a surprise. Hopefully that means something to somebody. But anyway, it was one of my 12,000 million shocks. I'm this way for good reason. Okay, so magnetic fields store energy. And what a point of telling about this is because the mechanism whereby energy moves from circuit to circuit is electromagnetic. And the energy is moving by way of the electric and magnetic fields between the two circuits. So it's not just jumping magically, it's migrating, and it can move in the fields. Okay? To make this happen, and I've showed you a little bit about transformers, and I'll go into them more in a minute. A little bit about transformers. To make transformers work, and transformers are the devices that move power from circuit to circuit. They actually become part of more than one circuit, typically two circuits, but you can go beyond two if you want to. For them to move power, they need to provide the connection between electricity and magnetism that allows energy to move from circuit to circuit, and that involves change. In short, change in movement. We already saw that an electric charge that is just sitting there, motionless, is purely electric. Is that totally true? Pretty much. So just a static electric charge sitting around on your sock. Magnetism is completely irrelevant. Once you move that charge, it becomes magnetic as well, because now you have a current. You have an electric current. Electric currents that is moving electric charges create around them a magnetic field. The structure of the magnetic field is complicated, not worth trying to remember, or me trying to convey it to you. So moving charge is magnetic. We will discover shortly that changing electric fields are also magnetic. Changing magnetic fields are electric. They're all interwoven all of a sudden. But the point is that they're all interwoven by change with time. Time is a crucial element. In setting off to teach this course years ago and to write a book for it and stuff, I felt very hamstrung by still photographs and artwork, things that didn't change with time, because physics is changes in time are so important to physics. If all you can do is live with still images, you can't move, you can't do anything. So motion is crucial. Where this connects then is the current that flows through a flashlight, which we've seen to this point. The current driven by a battery is described as being it's named, I should say, it's not described. It's called a direct current, meaning that the current always flows the same direction. And even more, typically, not only is it flowing in the same direction, but the current never changes with time. It's just steady. It's completely boring. The current in a conventional flashlight, when it's working properly, is just, it's the same now as it is now, as it is now, as it is now. Nothing's changing. There is moving charge, that is true, and so there is a magnetic field in the flashlight. It's boring and mostly unnoticeable. It's there, but that's for the experts, okay? Who cares? To get some real action going between the currents in two circuits and have energy move from one to the other, power move from one to the other, you need change. And the change comes about in the world of our electric power grid as what's known as alternating current. So whereas direct current means the current is always going the same direction through a circuit, and typically, not only is it the same direction, but it's the same amount of current. Nothing's changing. In alternating current, that's not true. Alternating current, the direction in which the current flows reverses periodically. Typically, the reversals are very smooth, and the current goes first one way, slows to a stop, then goes backwards the other way, gets faster and faster, and slows to a stop. turns around, goes backwards faster and faster, and slows up. It's smooth back and forth. And the smooth back and forth functions that show up naturally in nature are the trigonometric functions. You've encountered these before, like sine of time, approximately sine of time, with some constant in there associated with time to give it a rate at which the thing goes back and forth. But if you remember the sine functions or the cosine functions, they vary with time in this very smooth way. Does this have my laser conked out, of course? Yeah. Victorian approach here, right? Oh no, it crashed. I have to reboot it. Okay. Too many shocks. Okay, so as a function of time, as time goes by here on the right, the current and or voltage, we'll come to that in a second, goes first up and then down through zero, back and forth and back and forth. That's the world of alternating current, and it follows sinusoidal stuff. Why would there ever be sinusoidal currents in a desk lamp? You plug in your old-fashioned desk lamp, or alternatively something else, a toaster, something that uses a simple metal filament. Toaster uses just a metal filament. So the heating element. When you plug the toaster in, which is what I've got here in the drawing, the current that flows through it is propelled through it by a difference in voltage between the wire that delivers the electric charges, that sends current to the toaster, and the current that takes current back from the toaster back to the power company. And so the two prongs on the toaster's plug. Hopefully you've all played with it. You've encountered toasters before, or anything like a toaster. It's got two prongs on the plug, right? Maybe a third that's cylindrical, but let's set aside the third one for a second. Those two prongs plug into a conventional outlet in the United States. Their equivalents in all the other countries have a limited assortment of alternative structures. But in those two prongs, in the old days, those two prongs were identical in appearance. For the past many years now, most of my life actually, they have been subtly different. One of the prongs is a little wider than the other. I hope you've noticed that. You try to plug in the widget into the wall socket, and you have to flip it over because it doesn't plug in the first way. You know this? Remember this one? Those two wires are plugging into two electrical connections in the house wiring that provide different voltages. The wide one connects to a contact in that wall that sits at pretty much 0 volts, where 0 volts is the voltage of the Earth. That is, charges on that connection can neither release nor require. It takes no significant power to move, or energy. As I say, I struggle with using the word energy versus power. I'll leave it. It takes no significant energy to move charges from that wide slot to the ground, literal ground, or the opposite. They're pretty much at the same energy per charge, the same voltage. Is that okay? The other slot, the narrower slot, is different. Let me name the wide slot has a name. It's called neutral, which makes sense. It's pretty much neutral voltage. The narrower slot is called power, and it is different. Its voltage frequently differs considerably from neutral and therefore from the voltage of the Earth. Oddly enough, though, it's not consistently some other voltage. It's actually alternating. It goes first up. Let's pick a time. Starting now, it's an increasing voltage. It goes up sinusoidally, not surprisingly, peaks, and then it comes back down in voltage as a function of time. And how much time are we talking about? We're talking about 120th of a second, sort of in that range. Pretty short. It goes whoop up in voltage, and then it comes down. It goes right through 0. There's a moment at which it's at 0 volts. And then it swoops down into the negative range. and goes down to an upside down peak and then comes back up through 0 and then it repeats over and over rhythmically. So the voltage of power is bouncing up and down, which seems like an insane thing to do. Why would you do it? How would you do it? It's weird. It turns out to be very useful, and it's powered our electric grid. It's worked for 140 years, give or take, something like that. Incidentally, if you ever get into the wiring in the wall and stuff like that, by convention, the wire connecting to neutral should be white, and the wire connecting to, yeah, you can guess this. It's politically incorrect, but it's the way they did it. The wire connecting to the narrow power is black. Actually, maybe that's not so bad, black power. Okay. In any case, you pay attention to those wires, because if you touch the white one, you're touching something that's typically at 0 volts. And if you then touch a pipe or the bathtub water or something like that, you're probably fine, because there's almost no voltage difference between the two. There's almost no electric field in you to push charges through. Don't touch black and do the same thing. Much more nasty. I mean, it bites, okay? Because now there's big voltage difference between it and sort of everything in your environment. Okay? So those two wires, so power is going up and down and around neutral. There is often a third connection, which you've seen, the three-prong plugs. The cylindrical plug is literally ground. It is supposed to be connected to a spike driven into the ground, like a copper spike shot into the ground 10 feet. It should be really the voltage of the ground. And the reason for having it is because it's a nice safety feature. If you connect the frame of, say, your washing machine or your stove, if you connect the metal frame to that ground wire, which is green inside the wiring system, green, the color of the earth, at least the way it was before global warming. All right. Too many shocks. Yeah, I'll stop blaming it on that. If you connect the frame to ground, if any wires get loose inside the washing machine and touch the frame, they will exchange charge with the earth and not with you. It typically will blow circuits and blow circuit breakers and stuff for safety reasons, but it has been for a long time a useful safety feature. Okay, well, with this funny fluctuating voltage on the power wire, that means that the electric field in the wiring of your toaster is reversing, and it reverses many times per second. That means current flows first one way. Current always flows through just simple wires. It always flows from higher voltage to lower voltage. We've talked about that before. It's going from higher energy to lower energy per charge. So it goes from high voltage to low voltage. So when power is in the positive voltage ranges, current flows out of the power slot in the outlet through the wires into the toaster, through the toaster filament, and then back out neutral. When the voltage of power is below 0, current goes the other way. Current actually originates in neutral, the neutral part. The current flows out of neutral through the wire, through the toaster's filament, and departs your toaster land by way of the power wire, because it's the lower voltage at present. So current's going back and forth. In the United States, the number of complete reversals of the voltage difference between those two wires is 60 per second. So that means that the voltage goes from, let's start at a certain point. Let's start at maximum positive voltage on the power wire. It goes from maximum positive to maximum to the largest negative value back to the maximum positive value. That's one full cycle. It does that 60 times per second. In Europe and some other countries, it does it 50 times a second. It was a choice, and somehow or other we made different choices. This does have some effects on certain pieces of equipment that are sensitive to the rate at which that reversal occurs. All right? I will also point out that there are moments when there is no voltage difference between the neutral and power because power is on its way swooping through from positive voltage to negative voltage or negative voltage to positive. There are moments when there is just no voltage difference and therefore no current in the wires at all. And that's an issue. What else do I want to say to that? It's an issue for stuff that cannot take even a moment's absence of electric power. Things like your computer. Your computer cannot function without electric power. 1/1000th of a second of no power, it's done. It crashed. So it has to store energy for operating between those moments. With portable computers, laptops and stuff, it has battery as well. So the battery carries it through these moments of no power. For desktops and stuff, they have other storage devices inside to hold power for the dark moments. For lighting, you need that. It depends on the lighting. It depends on the stuff, but there are lots of energy storage devices that exist in part to survive those moments of no power. So that's alternating current. There's other nuances involved and stuff like that, but this is good enough. This is just a summary of things I said before. You complete 60 cycles per second in our country. You can often hear that 60 cycles corresponds to, if it is sound, it corresponds to a particular low tone. And you have heard that tone and tones related to it in the slightly malfunctioning electrical devices that are around us, the hums of transformers and other electronic machines. Some lights hum at 60 cycles, 60 times per second. Again, in Europe, it's 50 cycles. They have a different pitch driving them crazy. We have our own choice. Okay. Any questions about AC, alternating current? It's just DC, direct current, that's the one-way current flow. AC, obviously, the alternating current. And now you can start a band. Okay. The use of AC allows for the use of transformers to move power from circuit to circuit. And that is the point of this story here, or a main point. So how do transformers move power from circuit to circuit? And the answer to that, well, it's a long story, but a key part of the story is because the currents are magnetic. We've already seen that. That electromagnet is an example thereof. If the current changes with time, then the magnetic field changes with time, and changing magnetic fields produce electric fields. It's a little bit of a long story, but let me do it instead of just doing it, waving my hands in the air. Let me do it flat on the floor. Not a good idea, but let me do it in the context of. Well, I'll start with a simple electromagnet. So this is an electromagnet consisting of some iron and a coil of wire that connects to the electric power company by way of that two-prong plug I described moments ago. And therefore, it has, when I press this button, the switch to finally complete the full circuit, it's going to have one end of the coil connected to neutral and the other end connected to power. So power, neutral is going to sit there at 0 volts. Power is going to go up to positive voltage, down to negative, up to positive, down to negative, up, back and forth. And current will therefore flow through the coil, which is wrapped this way. It'll flow first one way and then the other way, back and forth. And it reverses for 60 complete reversals per second, which means it's 120 individual reversals. Is that okay? So that's going to become magnetic. But it's going to become magnetic in a weird way. It's going to become magnetic first north pole up as the current flows one way. I think it follows a right-hand rule that if the current's flowing this way, that's north pole. And then when the current reverses, that's going to become a south pole. So this is going to go from north, south, north, south, north, south, north, south. And with it, the magnetic field that comes out of essentially a bar magnet, it's going to be a north pole. When it's north pole here, the magnetic field's like this. And when this is a south pole, the magnetic field's like that. It's reversed, back and forth, back and forth. magnetic fields can be changing with time. And magnetic fields that change with time produce electric fields. And those electric fields can do interesting things. And I showed you some of these ones. Let's do them again anyway. So this is the world's simplest circuit. It's just a piece of aluminum, a ring. But you can make current flow in it. How would you ever make current flow in it? Expose it to an electric field that goes around, that points around in a circle in its direction. That'll push current through it first one way, and if that current reverses, then the current will reverse as well. This thing will therefore, it'll carry current if it's exposed to the right kind of electric field, and that current itself will be magnetic, and you can think of the magnetic field that's this electromagnet and the magnetic field of this coil of wire. They'll talk to each other, and that guy will jump. Okay? The whole story is a little more complicated, but that's the basic source of that motion. This guy does pretty well too. Oh, stop. The hum, that's the 60-cycle hum I was telling you about. Stuff starts to shake because there are big forces on this as it's going, and it's magnetizing and unmagnetizing. The switch sticks. Okay? So the details of why this guy jumps, a little complicated, but the basic idea is this thing creates a fluctuating magnetic field, north, south, north, south, north, south, and that produces an electric field, drives current through this wire, which is just a ring, and it becomes magnetic, and the two of them, they repel each other. If instead of using a single ring like this where you can't really see the current, all you can see is the magnetic influence of one on the other, we can switch over to this, which is a second coil of wire with a light bulb as part of the circuit. And this time, so electric power is now moving from this circuit to this circuit with no electrical connection between them. They are insulated objects. So this thing is running at 100, this is running a power line, and I would not want to touch these wires. I'm here holding these wires. I mean, I guess it's not great evidence. If I were really brave, I would grab hold up here, and I'm not that brave. Okay. So I hope you can see that there are two circuits here. This circuit, which includes the power company by way of this wire, and this circuit, which I'm holding in my left hand, and nothing else. It's a complete circuit. If it weren't a complete circuit, it would be boring, the light bulb wouldn't light. But it's a complete circuit, and it lights up. Any questions about that? The full mechanism, how the power is moving, just to walk you through it once. I've done it to an extent, even with these rings. When I connect this with the power company and create a complete circuit, this becomes an electromagnet. Very similar to that electromagnet over there, except that's a DC electromagnet. That has equipment on it to make sure that the current runs one way and very steadily. This is not. This is an alternating current electromagnet. It's magnetizing back and forth, back and forth, back and forth. Incidentally, because it's magnetizing back and forth, that means that it builds up a magnetic field first one way and stores energy. And then that magnetic field diminishes. And as it diminishes, the energy goes back to the power company. This is what's known as an inductor. The reason, if I just put a wire from this point to this point and skip the coil, and I press that switch, we would blow a circuit breaker, blam, or some piece in this arrangement would explode, because there would be no consumer of electric power. I would be taking in charges at high voltage, returning them at low voltage with nothing in between that is meant to take the energy out. The inductor is serving that purpose. The inductor is taking that energy out and doing what with it? Turning it into a magnetic field. And it can only do that for a very short period of time. You do not want the current to keep flowing in the same direction for very long, because if you do, it will have built up as much magnetic field as it can handle, limited by the iron actually, and then the wires will explode. So for 120th of a second, it's okay. For 120th of a second, the energy goes whoa into the magnetic field, it builds up, and then the energy comes back out and goes back to the power company. And oddly enough, the power company is aware of this, in effect, they have to deal with what are called inductive loads, stuff that's connected up to the power grid that has this behavior of taking energy in during half a cycle and returning it during the next, actually it's a quarter cycle. It comes back and forth, and there is hardware up on the power poles to deal with, where the power company is trying to deal with people who put stuff like this on the, plug it in effect, and are storing and returning power. They have to compensate for it. But in any case, the energy is going in and out of that inductor, and that's okay. When I bring this over here, I steal some of the energy from that magnetic field, and instead of going back to the power company, it goes into the second circuit. And how that's happening is because as the magnetic field is changing with time, it is creating an electric field, which pushes charges through that wire. The magnetic field is there right where the wires are, and it pushes charges around them. And just as a voltage drop creates an electric field to push charges through a wire, an electric field can itself create a voltage rise in a wire. If you just put a wire, just a chunk of wire, anyway, you know what, there we are, wire. This is experiencing voltage rises. Charges actually can move through this wire, push forward by the electric field, and come out at one end with more energy than they started. They can have energy added to them. And this is just a grand glorified version of that. The charges in that wire pick up energy as they're pushed in the direction they're moving by the electric field, and they drop off that energy a little later in the light bulb. And I said on a week ago Friday that any of you who have things like rechargeable, cordless toothbrushes, there we are. You know, the toothbrushes where you just sit it in the stand, and miraculously it powers up. Or your cell phones. Many of you may have cell phones where you just plop it down on top of some flat gadget. Lights come on, it blinks at you and stuff, and it recharges your cell phone. How's the energy moving? Same thing. You're assembling a transformer. Your cell phone is this piece. The stand is that piece. All right? I'm hooked. All right. Fun and games with transformers. Any questions about the concept of a transformer before I plow forward? Okay. So that's a transformer where I got the coil on the bottom, coil on the top, iron in between. Why the iron? Because the iron strengthens the magnetic field. It allows you to move more power from one coil to the other. I'm being fast and loose with the details, but that's pretty much the main thing. You can make, and I'll show you you can make transformers with no iron. They're a little trickier because the magnetic field can't store as much energy. You have to operate them typically at higher frequencies. Don't force the magnetic field to store energy very long. So this is a simple transformer. One coil is going to go to the power company, like there, okay? Chunk of iron to handle the magnetic field. Second coil, no electrical connection between the two. I'll complete the iron, actually, in this case, is a ring of iron, which is particularly, works particularly nicely. That full ring, there's no ends to it. It makes for a more energy efficient transformer. And these light bulbs are now completing a circuit that involves only that coil and nothing else. They're not electrically connected to anything else. And yet, power is going into them. It's going by way of the changing magnetic field in that iron, and creating an electric field over here, which pushes charges through the wire and lights the light bulb. And there's actually, just for fun, there's yet another coil here with a little light bulb on it. That's a third circuit in this gadget. So transformers can have two main circuits, but they can have more. By convention, the circuit in which the power arrives in a transformer is typically called the primary. And the circuit by which the power leaves the transformer is typically called the secondary. Do the names matter? Nah, but I tell you anyway. Okay, so this is a transformer that's taking energy out of a modest current at a modest voltage from the power company and delivering it as a modest current at a modest voltage to the light bulbs. In following rules that I probably will have to talk about next time. If you shorten the primary coil, the secondary coil, don't make it travel around the magnetic field as many times as the primary coil did. In that case, the amount of work done on every charge in the secondary coil is small because the charge doesn't travel very far in the direction of the electric field. There are not that many turns in the coil. Okay? So the charges don't take out as much energy per charge in going through. They come out with a smaller voltage rise having gone through that coil. Each charge picks up less energy out of this system, but you can send more charges through. And the point of that is, this is what's called a step-down transformer. It takes power from the power company in this case, and it delivers that power as a huge current with a small voltage difference. And can you see the nail starting to glow red hot? That's because we're running so much current through this that a nail can't handle it well and heats up terribly. So you can imagine this is how welding is done. Some amount of welding is done, okay? So that's a step-down transformer, and I'll come back to it. But let me show you a step-up transformer. Getting this apart, it magnetizes to some extent, and you have to yank it apart. Okay, this is a step-up transformer. The secondary coil now has many turns. As a result, each charge that goes around that secondary coil is pushed forward by an electric field for a very long distance and gathers up a lot of energy. So it leaves way more energy per charge than it arrived, and therefore comes out with a much higher voltage than it arrived at. And the result is, the voltage is so high it breaks down the air. It actually can just drive charge. The spark is rising because of hot air rises. But it starts at the closest approach. This guy bites, so don't touch it. You can play with it, but don't touch. Okay? It's the Jacob's ladder you've seen in all the Frankenstein-y movies. Ooh, that's science. Ha ha. Okay, I'll stop that for a second. And then go to the extreme case. And years ago, I built one of these guys. This is the professional version, much better. It's called a Tesla coil, and it is a transformer again. It's actually more than one transformer, but it's basically a transformer with a small number of turns in its primary, and you see them here, and lots of turns in its secondary, and it also starts at pretty high voltage. So it creates very high voltages. And it has no iron. It's an air core transformer. Therefore, it has to operate at much higher frequencies to be efficient. It's noisy, so be prepared. That's somewhere 100, 200,000 volts. The electric field around it is so strong that it drives charged particles through the fluorescent tube and lights up the tube without any contact. So there was a time when Tesla himself was trying to illuminate cities without any wires, using monster versions of that guy. One more time I'll do it. It's not very good for electronics, too. This guy is going nuts, but you get the idea. All right, I'll bring it back next time. We can look at it more carefully. But talk to you again on Wednesday.